Hey everyone, welcome back to Calculus 1. This is going to be lecture 4 in our Calculus 1 series, and in this lecture we're going to discuss the concept of continuity. Continuity, it turns out, is well, it's a very important concept to calculus in general, and when you get into your real analysis course later, you'll spend a lot of time rigorously developing theorems involving continuity. What we're going to be interested in for calculus is just having a good understanding of what it means for a function to be continuous, either overall or on an open interval or a closed interval or something. So we're going to have a couple of we're going to develop some intuition about it, and then we're going to develop some kind of more basic definitions of what continuity would mean, and then ways to look at functions and or regions of functions and determine if the function or the region is continuous. So with that, let's go ahead and get started. And so this will be section 1.4. Continuity. All right. So let's go ahead and kind of flush out a little bit of a definition here. So when we say that a function is continuous at a point, so when we say that f is continuous at a point x equals c. Sort of the everyday interpretation of this idea is that there are no the everyday interpretation is that there are no holes or gaps. Okay, so is that there are no holes, and of course that's a loose term, or gaps, or you might even use the word breaks in the function at c. Okay, so when we say f is continuous at a point x equals c, sort of the everyday interpretation is that there are no holes, no gaps, no breaks in the function at that point. So let's just take a look here. Let's take a look at a couple of scenarios. You could have a scenario like this, right, where you've got the function kind of coming down, you've got a hole, and then it continues on. Right, so here you would say, and if this is x equals c, we would say f of c is not defined. I.e., there's a hole, there's just nothing there. Another scenario that might occur would be, something like this. Maybe the function comes up and you've got a gap, and then the function continues on, and so here would be like c. And so in this case, yes, you've got a hole, but you've also got a scenario where the limit doesn't even exist. There's no agreement on either side. The limit as x approaches c does not exist. Right, and it could also be the case that maybe the function is defined at one side, at c, but the function doesn't exist, or the limit doesn't exist. Okay, another scenario you might see with these, it would be something like this, where you've got the function kind of trucking along, you got a hole, the function is actually defined at the hole, right, is defined at c, but in this case the limit of the function at c is not equal to the value of the function at c. So each of these instances are examples where a function is discontinuous. These are examples of discontinuities. Okay. Or, so discontinuous just meaning not continuous. So again, so here we had a situation where f is not defined at x equals c. Here's a condition where maybe x is defined, or f is defined at c, but the limit doesn't exist because you've got this kind of break or this gap here in the function. And the third option here is where, yes, where f is defined at c, but the limit is not equal to the value of the function. Right, so these are kind of the three sort of big scenarios that you would encounter if you were dealing with a function that's discontinuous. And another example might be asymptotic behavior, which we'll see in a little bit. Okay, so let's kind of crank out a definition here. And so this definition, what we're saying is here's a function f is continuous at c, okay, if the following three conditions are met. Okay, the following three conditions. The first condition that needs to be met is that the function has to be defined at c. So the function has to be defined. The second condition is that the limit as x approaches c of f of x needs to exist. Okay, so there has to be a limit at c for the function. And then the third condition is that the limit as x approaches c of f of x needs to equal f of c. Okay. So if you have these three conditions, if these three conditions are all simultaneously met, then you have a continuous function. So let's take a look at these examples here. So looking at this example, what's the problem? Well, condition 2 is true, right? The limit does exist, right? But condition 1 and 3 are not met, right? First of all, the function is not defined at c, and second of all, clearly the limit can't be equal to f of c since the function is not defined at c. What about this one? Well, here the function is defined at c, but the problem is that the limit doesn't exist. Right, your left and right hand limits do not agree, so you have no overall limit. Right, and consequently, the third condition is also not met because the limit doesn't exist. What about over here? Here you've got the function being defined at c. You actually have the limit existing. Right, the limit definitely exists here, but what's the problem? Well, it's spelled out here. The limit of the function at c does not equal the value of the function at c. All right, so continuity is, in each of these three cases, continuity is, the functions are not continuous because one or more of these conditions are not met. Okay. Let's take that definition and expand it a little bit and talk about continuity on an interval. So this will be kind of obvious, I suppose, but it's important to be thorough with some of this. So we say that a function is continuous on an open interval okay. The open interval, let's just call it AB, if it is continuous at each point in the interval. Okay, so a function that is continuous on the every point in AB, so any point in between A and B, you would have the three conditions of the prior definition met. If that's the case, then we can say that the function is continuous on the whole interval. Kind of natural, right? And just kind of blowing this up a little bit and saying, so if f is continuous on the entire real line, so something, I guess you could kind of notate it like this, from negative infinity to infinity. We say that f is everywhere continuous. Everywhere continuous. Okay. Very good. Okay, so this idea of continuity is a very well-defined idea based on these three conditions. These three conditions have to be met in order for a function to be considered continuous. And we can expand the definition of continuity to describe entire intervals. And basically, an interval gets its continuity from every point in the interval having met the criteria of continuity. And then we can say that a function is continuous for all real numbers if it's true that the open interval from negative infinity to infinity, every point in there would meet the criteria of continuity. So there it is. So if the next thing to discuss is if a function f is defined on an open interval I, except possibly maybe at a point c, and f is not continuous at c, then f is said to have a discontinuity at c. So this is kind of a definition of discontinuity. So if a function f is defined and so if a function f is defined on an open interval I, and then we can say except possibly at a point c, right, c in I, so some point in c, and f is not continuous at c, then we say that f is said to have a discontinuity, okay, at c, right? So this is just so if you have a function that is defined on an interval, except possibly at a single point c, if you have a function defined on an interval, but there exists a point in there where f is not continuous, then we call that point a discontinuity. So kind of a simple, just kind of a visual would be something like this, right? Okay, so if we take this to be A and this to be B, right, so then you can kind of imagine that region. Well, the function f is defined on that open interval A to B, right? Everything in there is defined except at the point C. We see there's a hole at the point C. I'll put that in there. Sorry, I should put that in. Okay, so f is defined on A to B except at C. So what we call C, so C is a discontinuity. All right, so like basically all those little holes at places where you have where you don't have continuity, you have what's called you have what's called discontinuity there. And discontinuities they kind of come in two types. Okay, so you've got two types. You basically got what's called removable and non-removable. All right, so removable and non-removable. So what do we mean by these? Well, so a removable discontinuity is a discontinuity that can be made continuous by an appropriate redefining or possibly defining of the value of the function at the point. Right, so let's talk about removable first. Yeah, so let's see, a discontinuity at C is called removable. Right, it's called removable if f can be made continuous by an appropriate redefining of f of c. Okay, so you got this point C where you've got a discontinuity, but that discontinuity can be considered a removable discontinuity if it's possible to redefine f at that point, at that one point, such that it becomes continuous. Right, and so this would be a great example of a removable discontinuity. Right, so all I've got to do here is redefine f at this one point, and then the function is continuous at that point. Right, you can kind of think of a removable discontinuity as a discontinuity where basically I could take one point and sort of plug the hole. Okay, so another example might be of a removable discontinuity might be something like this, where let's say I've got a function that kind of comes up like this. I got a hole and it goes along, and then for some reason the function is defined differently here at C. All right, so this would be an example of a removable discontinuity. What I would have to do is I need to redefine f of C. Right, basically what I need to do is kind of redefine f at C such that the hole gets kind of plugged. Okay, so these are kind of the easy discontinuities. They're the discontinuities where you basically have a single point out of place, or a single point that doesn't exist. Okay, now contrast that with non-removable. Now non-removable basically is the definition of non-removable is just that it's not removable. I mean, I'll write it, but non-removable discontinuities are not removable. That's kind of a silly thing to write, but okay, so kind of a definition there. Example of that would be something like consider like f of x equals 1 over x, for example. That's a good example of a function with a non-removable discontinuity. We know that the function is not defined at x equals 0, so it's not defined at x equals 0. Now if you look at this function, it'd be kind of obvious why this discontinuity at x equals 0 is not removable. So as you approach 0 from the right, the function goes like this, and then it shoots up to infinity. And as you approach 0 from the left, the function does something like this. Right, so there's no way to redefine f at just the point, at just the value of 0, x equals 0, such that you accommodate for the fact that these two head in opposite directions. Right, you're not going to get continuity by redefining the value of the function at a single point. Right, namely because this one decreases without bound on this side, it increases without bound on that side. The limit will never exist no matter how you define the function at 0. Okay, so that's a good example of a non-removable discontinuity. Let's develop a concrete example of removable. So let's consider we'll say g of x equal to x squared minus 1 over x minus 1. So what does this look like? Well, let's draw it quickly here. So if it's xy is here, looks like this guy kind of cuts through maybe x equals 1 area. And it kind of goes like this. This turns out to be a straight line, and it heads up a ways, and then you've got a hole. Right? So just like by looking at this, you can see that this is the kind of situation where you've got a removable discontinuity at x equals 1, right? Because it's basically a single hole. Otherwise, this looks like a straight line, right? So the domain of this function is all real numbers, obviously, except for x equals 1. And obviously, this has this discontinuity is removable. So how do we go about redefining the function? Well, what we could say is the following. We could redefine g as, let's say, g of x equals x squared minus 1 over x minus 1 when x is not equal to 1. And we could set it equal to, this is supposed to be at 2 when x equals 1. Right, now see, if you do that, if you redefine the function like this, then you get continuity. Right, specifically you can see that in this case the function is defined at x equals 1. Okay, so item 1 is captured. The limit already existed at x equals 1. Right, so clearly you can see that the limit, it would approach a certain point and jump over that point and then continue on. Right, so clearly the limit exists there. And then now, since you've defined it as such, the limit is equal to 2 and the function is equal to 2. So all three conditions are met. So g is defined at x equals 2. The limit of g exists at x equals 2, and the limit as x approaches 1 of g of x equals g of 1. Okay, so those three conditions make g continuous, and the way we did it was by redefining the function specifically at this point, x equals 1, and redefining it in such a way that you get continuity, of course. So aligning the value of the function with the limit at that point. Okay, so it's usually very easy to see, especially if you plot a graph or a function. If you plot the function and examine it near the discontinuity, it's very obvious almost always if the function is, if the discontinuity is removable or not. Okay, very good. So we've talked about continuity, we've talked about lack of continuity, we've talked about different types of discontinuities, removable, non-removable. Let's expand our idea of limit a little bit. We've kind of discussed this informally, I'd say, but let's be a little more formal with it. So far we've discussed overall limits, but let's take a look now at what's called a one-sided limit. The one-sided limit. So we talked about kind of like, we've sort of discussed this already, but just like informally. So we talked about, if you have the xy plane here and maybe your limit point is here at 0, we've talked about what happens to the function as we move towards the value of c from the right-hand side. And this is what we would refer to as a right-hand limit. And we would denote it like this. So let's say this is the point C. So we would denote this as x approaches C from the positive side. We call this a right-hand limit. Okay. Let's just say that's equal to L. Okay. So as we approach it from the right-hand side, now you could also have a similar situation where you've got your C and you're approaching it from the opposite direction. And that we would call a left-hand limit. the limit as x approaches c from the left-hand side, or the negative side. Okay. All right. So this would be called this is the right-hand limit, and this other one is the left-hand limit. So those two, I mean, intuitive, right? One's coming from the right-hand side, the other one's coming from the left-hand side. Okay, let's see an example of something, you know, what we can talk about once we have this idea. Let's consider the function f of x equals 4 minus x squared, the square root, and let's identify the limit, the right-hand limit. The right-hand limit of this, right? So this is a weird function here, and so the way this looks, if we plot it, right? So first of all, this is a function that's not everywhere defined, right? So just taking, let's see, this would kind of come through. And so you'd have, this is basically like going to define a semicircle. Okay, so you've got a function that's going to start over here, and it kind of comes up like this, goes through y equals 2, and then down to x equals -2. So this would be the point -2, 0. Right, and this would be, of course, 0, 2 up here, and this would be 2, 0 over here. And so the question would be like, well, what is the limit as x approaches -2 from the right of 4 minus x squared? Okay, so normally, like the function kind of ends here, right? This is sort of the edge of the domain of this function, right? Because it begins to kind of wrap around itself here, right? So the function, you know, the idea of a function is that you have to pass the vertical line test, and so in order for this to be a function, you have to constrain the domain down to -2 to 2. And so the question here is, well, what happens? What's the limit at -2? Kind of what's the limit at the left-hand side of the domain, which normally doesn't make sense in the context of a normal limit, because you have to have an open interval around the point that you're around the limit point. But in the case of a left-hand limit, it's perfectly reasonable to say what happens to the value of the function as we get infinitely close to x equals -2, and specifically from the right-hand side, right? So as we traverse the x-axis and we get closer and closer to this point, what happens to the value of the function? Well, I mean, quite obviously, in this case, it's 0, right? So no reason to get super analytical with this one. This one is more just an intuitive idea. Like with the left and right-hand limit, it is possible to look at points that border the domain of the function, right? Without any kind of problems. So that's an example. Here's another example. I think I'll have another sheet for this one. Start fresh. So let's talk about this function, which people may or may not be familiar with. So consider the function f of x equals x, but the truncation function. Right, so this function, let's draw a picture here of what this thing does. So what this basically does is it's defined for any x, for any real number x. So what happens with this function is you plug in a real value, you plug in a real number x, and what you get out of this is an integer. And so what it does is it basically truncates anything to the right of the decimal. Right, so for example, f of 2.36 would equal 2. F of 3.5 would equal 3. F of 4.99999 would equal 4. Right, so just truncating the decimal expansion. And so you can imagine what this looks like, right? Let's say this is 1, 2, 3, 1, 2, okay, and then 1, 2. We'll just draw a couple of checks in here so we can see what this visually looks like. So at 0 it's defined, and then it comes along here, and then you've got an open gap there, and then it jumps up, right, and it goes over, and you've got a gap, and then it jumps up and it goes over and you've got a gap, right? And then similarly down here it would look like this. Okay, so you can kind of see that it's defined everywhere, right? You've got a lot of gaps, but that's because you've got these jumps, right? So every value in every real number is defined for this function, but it is got a lot of discontinuities, clearly. So first of all, are these removable discontinuities? No way, right? There are an infinite number of them, first of all, so the function would have to be redefined at an infinite number of discontinuities to even think about it. But then additionally, there are gaps here, so there's no way to plug this hole and also have the line sort of, and also have the limit agree left and right. But in this case, we can talk about, let's look at the limits of the function as x approaches 0. Okay, from the left and from the right. So the limit as x approaches 0 from the left-hand side of this function x. Well, what would happen, right? So we're approaching 0 on the x-axis, right? So first we'd be down here, then we would jump up here. And now as we get closer and closer to 0, what do we get? Well, we would be down here, right? And as we get closer and closer to 0, the limit would look like -1. Right? Now, what happens as we approach 0 from the other direction? From the positive direction, right? So now we're on the x-axis moving this way. So as we get closer and closer to 0, right, what happens with the value of the function? Well, first we would be up here, and then we would jump down here, and then we would jump down here. And as we got really, really close to 0, we would stay on this line here, and we get right up next to it. And so the value of the right-hand limit is equal to 0. Right? So this function has a discontinuity at basically all the integers, right? And it's a non-removable discontinuity as well. And really what you can say is that the limit as x approaches a from the right-hand side of the function is not equal to the limit as x approaches a from the left-hand side of the function. And this is for all integers. Okay, so the left and right hand limits do not agree at any integer. Right, so pretty much any integer is going to produce discontinuities. Okay, great. And so this example leads us to a nice kind of theorem about limits in general. And maybe it's as intuitive, but let's go ahead and talk it through. So a theorem, so let's go ahead and let f be a function. Let f be a function and c and l be real numbers. Okay. The limit of f of x as x approaches c is L. Okay, it's L if and only if. Okay, if and only if the left and the right hand limits are both L. Okay, well, so that seems like it should be reasonable, right? I mean, obviously, if the limit overall, so the definition of the overall limit basically said, look, as we approach the limit point C from the left and from the right, from either side, then the function has to approach L. Well, that's exactly what happens here, right? So if the left-hand limit approaches L as x approaches C, we call L the limit. If the right-hand limit, the function approaches L from the right as x approaches C from the right, then of course we say that the limit is L there too. So this is basically a slightly more thorough treatment of sort of the definition of a limit that we're used to seeing already, that we have seen already. So very good, very good. So a lot of times, if if you're asked to show that a certain limit is equal to a certain thing, it may in those cases be sufficient to demonstrate that the left and the right hand limits are both equal to the thing you're trying to prove. Okay. All right. So let's take another. Let's see. Take another definition here, and then I think we'll break the video into two so we don't have too long of a video. So another definition, one more definition in this. So we talked about continuity at a point, we talked about continuity at an open interval, and given left and right hand limits, we can now discuss the idea of continuity on a closed interval. So a function f is continuous on the closed interval AB, right? So you write that like that. If it is continuous on the open interval AB, of course, right? So you need that. And what you need is the left and right hand limits need to exist and meet the following criteria. So the limit as x approaches a from the right hand side of the function needs to be equal to f of a, and the limit as x approaches b from the left hand side needs to be equal to f of b. Okay, so basically, if you can imagine, what this looks like, right? Maybe you have something like this, where you've got a and b, and let's say the function moves between those two. Okay, so obviously, when we're talking about the open interval, right, then you don't have to ever worry about an end point of the interval. It's always open, right? So you've always got something additional. You can always kind of move closer and closer to the edge. But here you have a discrete edge, right, to the interval. And so everything in between, you got to have continuity, but then also you have to have left and right hand limits agreeing with the value of the function on the endpoints. Okay, so that is the idea of continuity on a closed interval. So it gets kind of weird, and in general, closed interval continuity is not usually something that people worry as much about, but certainly open interval continuity is important. Closed interval is just kind of like, I think a lot of times when you're taking Calc 1, you're kind of like, what's with all this open interval? Because you're possibly more used to thinking about closed intervals, and so this just kind of wraps that up nicely. It kind of gives you a quick sense of what's important, how the definition can be expanded to include the closed interval idea. Right, and it's just by basically having these two additional pieces attached to the criteria. So you got to have the open interval, and then those two endpoints that are the weird points in the set. Those two endpoints have to be dealt with specially. But you can see how this aligns nicely with the idea of continuity. All right, very good. Let's take one example, and then we'll in this part A of the video. So let's see an example. Let's consider the function f of x equal to 1 minus x squared. Okay, so this is similar to the one we saw before. I think it was 4 minus x squared. And so this is going to be that semicircle again. Okay, so you've got 0 here, and this is positive 1, and that's negative 1, and this would, of course, be 1 up there as well. So this function has a domain, as we said previously. The domain of f is equal to the interval -1 to 1. Okay. And obviously, just kind of by looking at this, all points in the open interval from, of -1 are continuous. Right? There's no problem here. There's no number. I can't plug a number into this and sort of get a discontinuity, at least, not in not the normal way of thinking. This is a squared term, so even when I plug in my negatives, I still get a positive, and they're always going to be less than 1, so that 1 minus, I always get a positive number in here, so not a problem. So obviously all of the points in the open interval are continuous. Now, what can we say about the endpoints? Well, we can say that the limit as x approaches -1, right? Here we're approaching -1 from the right of 1 minus x squared square root. Well, what's it equal to? Well, I mean, the visual would tell us it's equal to 0. Is that what we get? We plug in a -1 here. -1 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. So you get a 0. That's good. That's also equal to the value of the function, right? And the same thing is true as we approach the other side of the interval of the domain from the left, like so. And there too we get 0, right? 1 minus 1 squared is 0. Square root of 0 is 0. And of course, that's equal to f of 1. Okay, and so basically we can say that f is continuous on -1, 1. That's on that whole, on its entire domain. It's continuous. Okay. All right. So I think we'll end the video here, and then I'll continue it in a part B.